So welcome to the afternoon session, which is dedicated to the chemistry and science of materials. Our first speaker doesn't really need any introduction, but I will say a few words. In 1984, in Physical Review's Letters, there appeared a relatively small paper, which in retrospect marked a truly scientific revolution, because the paradigm that all crystals are packed properly, that paradigm was demonstrated not to be complete. As always is the case with revolutions, they do meet all sorts of criticism, objections, and that also held true in that particular case. But 27 years afterwards, the principal author, Professor Shechtman, went to Stockholm to pick up the Nobel Prize. Today he is going to recall part of the story and to enlighten us about the most recent news on quasi-crystals. The floor is yours, then.
But emphasized the role of transmission electron microscopy in the discovery and further development that are linked to transmission electron microscopy. So this is my name. That's the way I spell it, although several people have other ideas. I'm from the Technion, and also I have a position at Iowa State University. And so let us start. In the mid-80s, there were three surprising discoveries on the structure of matter and its properties. And they came year after year, and all three of them received the Nobel Prize later on. First came my paper with my colleagues on quasi-periodic materials. Then came Fullerenes, and then came 1986, high-temperature superconductivity. When high-temperature superconductivity was declared, there was no objection. Everybody was happy. Hey, we don't need liquid helium anymore. We can use liquid nitrogen for high-temperature superconductivity. When Fullerenes were declared, Harry Cortor, my good friend who passed away a couple of years ago, told me that there were 6 papers against his model, which is, by the way, also icosahedral, but they died very soon. But when our paper was published, hell broke loose. On the one hand, growing number of young avant-garde people who started to study quasi-periodic materials. They took my discovery and turned into a fast-growing science, and on the other hand, rejection, total rejection, and I will talk about it later on. So to make everybody equal here, those of you who are not in crystallography, I will explain very simply a few terms: order, periodicity, and rotational symmetry. So here we have a two-dimensional structure. Clearly, it is ordered. What does it mean to you? It means that if I ask you to continue this in this direction or in this direction, any direction, you know how to do that. Very simple. There is order. You know how to continue this. This is not only ordered, but this structure is also periodic. So there is periodicity in this direction, periodicity in this direction, periodicity in that direction. Every direction there is periodicity. This is because the structure is periodic. All right. So that's about periodicity. What about rotational symmetry? Here is the same two-dimensional structure, and I can turn it 90 degrees, and it looks the same. 180 degrees looks the same, 270 degrees looks the same, 360 degrees goes back to where it was, and because you can do it 4 times, and each time it looks the same, then this structure has a 4-fold rotational symmetry. Enough of that. Let's say a few words about crystallography. The science of crystallography really started many, many years ago. The Greeks had good ideas about the structure of crystals that were found in nature or grown in the kitchen, but there were no way to prove that these ideas were correct. But in 1912, experiment by von Laue, X-ray diffraction, the first X-ray diffraction experiment, we had the tool. We had X-ray diffraction, a tool to study crystals and analyze a lot about their structure. In X-ray crystallography became the name of the science, And the community that governed the rules of crystallography is called the International Union of Crystallography. This is the hardcore body of mathematical crystallographers, no-nonsense people. Everything has to be defined from the very foundation. Why am I saying it? You'll see later on. And so the science grew, and there were other means of crystallography to help us: electron crystallography in the electron microscope, neutron crystallography. And all these structure and all these hundreds and thousands of crystallographers studied hundreds of thousands of different crystals. And the one thing that was common to these crystals is that all the crystals that were found, hundreds of thousands of them, were ordered, and therefore crystals, and periodic. No exception. Okay, this was the story. And because of all these observations, not based on any theory, a definition of a crystal was something like this. This is from a book by Quality. The old generation studied from this book, X-ray crystallography. And it says the following: a crystal is a solid composed of atoms arranged in a pattern periodic in 3 dimensions. Simple definition. Life was simple. We felt that we understand everything about crystallography. Yes, you can find a new crystal, analyze its structure. Let's say that the new structure is DO19. Wonderful. We have a drawer of DO19. We have 2051 crystals there. Welcome 2052. Close the drawer. Everybody's happy. No revolutions were expected in crystallography. It was considered to be a mature science. Here's another definition by a book by Bart and Masalsky. This exactly the same meaning, different words. Atoms in a crystal are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. A crystal is ordered and periodic. Crystallography in 1982. Here's a page in the book of Charles Kittel. I know that what I marked there is too small to see, therefore I enlarged it, and maybe you can see it now. And it says the following: we can make a crystal from molecules which individually, that means every molecule, which individually have a 5-fold rotation axis. But we should not expect the lattice to have 5-fold rotation axis. Every molecule can have, but not a crystal. Okay, I will prove to you why this is the case. And so, here is an example of a periodic crystal. These are atoms in diamond. This is a picture that I took very many years ago in one of the first excellent high-resolution microscopes. Of course, today there are much better microscopes, and later in this meeting you'll hear about these fantastic high-resolution microscopes. So you can see that this structure is order, and it's periodic. So there is periodicity in this direction, periodicity in this direction, periodicity in this direction. Any direction you go, periodicity. This is real space. Okay. Now, let's say a few words about diffraction pattern from a periodic crystal, which is characterized by periodicity of the diffraction peak in the reciprocal space. The reciprocal space is a space where the diffraction space is alive. And we have to understand the reciprocal space in order to analyze diffraction patterns. And here's an example. This is an electron diffraction. It's basically a cut through the space of the diffraction pattern. And you can clearly see, because it was taken from a periodic crystal, the diffraction pattern is also periodic, and there is periodicity in this direction, and in this direction, and in this direction, periodicity in every direction. And the rotational symmetries that are allowed in the real space and in the reciprocal space are 1, 2, 3, 4, and 6, no 5, and nothing beyond 6. These were the rules in periodic crystals. These are the rules in periodic crystals. Nothing changed. And then something amazing happened. The International Union of Crystallography, remember, these hardcore mathematical crystallographers, no-nonsense mathematicians, they came with a new definition of a crystal. This new definition is interesting two ways. Number one, it's a poem. Hey, the International Union of Crystallography, a poem. Let's read it slowly, and you'll see the poetic value of this definition. It says, it doesn't say a crystal is. No, it's soft. By crystal we mean any solid having an essentially discrete diffraction diagram. And by aperiodic crystal we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. Hey, this from the International Union of Crystallography? What happened? But the other thing is, you may have not noticed, the crystal is now defined through the reciprocal space. It is a crystal if the diffraction pattern is that. We see the diffraction pattern and we say, this diffraction pattern comes from a crystal. While as before, the definition was based on the real space. Okay, 1982 was the 70th birthday of crystallography, and this is the year quasi-periodic material crystals were discovered. And this is the reason for the change in the definition. Let me take you through briefly through the afternoon of the discovery. I will show you a picture of my logbook, and this is the logbook. This is the day of the discovery, and this is the logbook. It was not designed to be seen by anybody else but myself, so everything is sloppy, but it contains a lot of information. And when I talk to young students, which I don't see many of them here, I encourage them to write in the logbook every experiment or every calculation that they make, because although they may remember it in the next couple of weeks, they will not remember it years ahead. So make notes. So what is the information it contains? First of all, the date. The date is April 8, 1982. The material is aluminum 25 weight% manganese. This is the plate number in the electron microscope. They were made of glass. The plates were made of glass. And this is plate number 7020. I know that this is the afternoon because the previous page is the morning of that, and I worked on a different material. So leisurely, I take SAD, selected area diffraction. I take a diffraction pattern, another one, picture with modification 28,000 times, 70,000 times, and then I arrive at picture number 7024. I take the picture, I look at it 36,000 times, and I will show you the picture, and I will tell you my reaction. And then I took another picture, selected area diffraction, I look at the diffraction, I count what's going on there, and I write tenfold. Tenfold means tenfold rotational symmetry with 3 question mark, cannot be. And from there on, I performed experiments one after the other, which I'll explain to you later because this talk is really about transmission microscopy. And I explained why I took all these pictures, what did I do here, and so this picture will come again later on in my talk. So this is what happened. And this is the discovery. And, you know, when Archimedes made his discovery, the story tells us that he jumped out of the bathtub shouting, Eureka. Now, we don't do that anymore. Today, when a discovery is made, usually the reaction is something like, hey, what's going on here? Or, wow, that's strange. What? This is the beginning of the realization that something different appeared in our life and in our science. Okay. So I'll show you the first view of the icosahedral phase. This is plate number 1724. This is the original plate. This is the original picture. So I look at it and I say, what's going on? I will explain to you why this picture is strange. First of all, what do we see? We see remember this is aluminum, 25 weight% manganese. It was made by rapid solidification. All my research those years were rapid solidification. So it's a polycrystalline material. Here's a crystal. This is one crystal. And this is the micron bar. So it's about half a micron in size. Something like this. These are small crystals, half a micron. So what is strange? What is strange is that this is a bright field image. It was taken by the transmitted beam of the microscope, and this is pitch black. And this is pitch black, and this is black, and this is black, and this is black. When you see that, as an experienced microscopist, you know that these crystals diffract so heavily that there is almost no energy left for the transmitted beam. All the energy goes to the diffracted beam. And I have never seen anything like this in my life. And I was an experienced microscopist. Nothing like this. And I say, what is the material that diffracts so heavily? And then I take a diffraction pattern for one of these. Let's say from this one here, just this. This you can do it in the electron microscope. You put an aperture in, concentrate on an area, and you take a diffraction pattern from that area. And I did that, and I received the following pattern. Okay, let's go back a little bit. I look at this pattern, and I said, wow, that's very different. What's going on? What is the rotational symmetry? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, cannot be. 1, 2, 3, 4, 5. Tenfold, all right? Turns out that it is really fivefold, but you cannot tell from the diffraction pattern. You have to take later on, as I did, a Kikuchi pattern, and that tells you that it's really fivefold. But that's besides the point at this moment. So, but this diffraction pattern doesn't only have a strange diffraction pattern, a strange rotational symmetry, but it has no periodicity. So if you look at this red line that I just marked here, you see that if you take the distance, let's say from here to here, and you multiply by 2, you get there. And there is nothing there. No periodicity, 10 or 5-fold rotational symmetry. What's going on? So I will explain to you what goes on in my mind. I say to myself, based on past experience, this must be a twinned structure with very small twins. I will show you examples and explain exactly what I mean by that. The ratio of distances between the central spot and the other spot is not a rational number, but it is the Fibonacci number tau, or phi, known also as the golden mean, and this is the Fibonacci number tau, 1 plus root 5 divided by 2. Of course, you cannot get this number by measurements. This came later from theory. Irrational numbers came into crystallography. They were not there before. Of course, you know, in the electron microscope, you can turn you can rotate, and you can rotate it, you can turn it, so you can reach different orientations. And this is what I did, and received all these diffraction patterns. So here is the fivefold. When I went so many degrees in this direction, I have twofold and fivefold again, and the distance between this and this is 63 degrees, and so on, and 5, 3, 2, 3 again. And these are the angular differences between the diffraction pattern. Because this ratio has an icosahedral symmetry, I called that phase, that at the time was not known very well even to me, I called it the icosahedral phase, because it had icosahedral symmetry, and I will explain to you what is an icosahedral symmetry in a few minutes. Okay, so this is what I thought I have. I thought I had twins, and here is an example of twins, in fact, fivefold twins in diamond. Now, diamond is, of course, a periodic structure, and what you see here is the following. This up here is a crystal. This is a different crystal, a different. 5 of them, different one. But there are boundaries between them. Ignore the sigma notations. This is not interesting at this point. But this boundary is not just any boundary. It's a very special boundary, because it's like a mirror that reflects this plane onto here. and this onto here, and this here, and this there. So these are like mirror images. Now, why did I think that I have something like this? Because of the following. If you take a diffraction pattern for one of them, clearly you will have a periodic diffraction pattern, because it's a periodic structure. Nothing special. If you take a diffraction pattern from the other one, you will have the same diffraction pattern, but rotated 72 degrees. Why? 360 divided by 5. And so on and so forth. So this is rotated 72 degrees to this 72 degrees, and so on. Now, if you take a diffraction pattern, which you can do in the electron microscope, from all of them together, then you'll have 5 superimposed diffraction patterns. 1, 2, 3, 4, 5. And clearly, if you do that, you will have a 5-fold rotation symmetry diffraction pattern, but it is not taken by one crystal. It is 5 different ones superimposed. And this is what I thought. I'll show you another example based on my purest experience, but before that I'll show you why 5-fold rotation symmetry is forbidden. And in order to prove it, there are many proofs. You can prove it many ways, but here is one proof which I like. Let's say that there is 5-fold rotation symmetry in periodic crystals. If so, let's take a plane in a periodic crystal in which you have 5-fold rotation symmetry, and choose 2 atoms, P and Q, and choose them in such a way that they are the closest atoms on that plane. Now, if 5-fold rotation symmetry is allowed, then you can take, and the distance r is the minimal distance, then you can take atom Q, which is right here, and start rotating it around P. 1, 2, 3, 4, 5, and there must be a Q prime atom there, if there is 5-fold rotation symmetry. Same with P, 2, 3, 4, 5, and there must be a P prime atom there, but you see that P prime, Q prime are closer than PQ, which cannot be because I chose the shortest distance. Okay, simple proof why 5-fold rotation symmetry is forbidden. Now, okay, you've seen this. Here is another example. This structure is also a twin structure. It exists in the aluminum iron system, very common. And what you see here, you can see in an electron microscope. These are large crystals, really large crystals. Optical microscope is good enough to study them. And what you have here are 10 twins. Look at, you can count the number of petals on this flower-like crystal. And these are all twins. Why does it have really 5-fold? Because the orientation of this crystal is exactly the same as this crystal. And this orientation of this crystal is exactly the same as this. So altogether 5-fold. Now, if you take a diffraction pattern from all of them, then this is what you get. All of them together. It seems like the diffraction pattern that I received with 10-fold rotation symmetry. You can count the point. But this is superposition. If you want to see just one of them, here's one. And if you do 5 of them, you'll get the diffraction pattern that I see. This is what I knew before. This is what I thought. And I said, okay, I will find the twins. I will define them. And in the electron microscope, you define very well the crystallography of the twins. You can define them, note them, forget it, because it's not interesting. And I spent the whole day, whole afternoon, trying to find the twins and could not find them. There were no twins there. I will describe to you a couple of experiments to show what I did that. Here is my logbook again. And now you can understand the following. I said, okay, let's look at the twins. This chain means that all these are taken on the same crystal. They're all taken from the same crystal. And these also from the same crystal. What you see here is a partial drawing of the 5-fold rotational symmetry diffraction pattern. And I took dark field images. What does it mean, dark field images? Remember, we talk about electron microscopy. It means that instead of using the transmitted beam to take a picture, you take one of the diffracted beams. And then if you use one of the diffracted beams only, then if you look at the image, you will see the part of the image that contribute to that diffracted beam. So this is called dark field experiment. So here is what I did. And here I marked, oops, right. Here I marked the number of plates. 1727 was taken from this point, 1729 from that point, and so on and so forth. Just so that I will recall what I did. Okay, so these are the experiments, and what you see here is that instead of finding small twins, the whole crystal is lit. No twins were found by this dark field experiment. Now, I said, okay, maybe they are very, very, very small, and this was not a high-resolution microscope. It was a Philips 400, by the way, for those who are interested. Let's make a microdiffraction. Microdiffraction in the electron microscope, what you do there is you focus your beam onto the smallest spot that you can, and on that microscope it's called 400 angstrom, 40 nanometers. This was the diameter of the spot. I could not get any smaller than that. And hit a point. And if that point contains just one twin, then I'll have a periodic diffraction pattern. If it contains two twins, I'll get 1, 2. But anywhere I went, I received the same 5-fold rotational symmetry diffraction pattern. No twins. I knew from day one, from that afternoon, that there are no twins. I did not know what it was, but I knew what it was not. And it was not twins. Why do I mention it? Because later on, years later on, the opposition claimed that these are twins. And I knew from that afternoon, no twins. Okay, let's continue. Later on, colleagues of mine from France. Why France? Because France has, at the time, the best high-resolution microscopes. These were based on high-voltage microscope, 1 million volts and even 3 million volts microscopes in France. Today, you don't need that, and later on, my colleague will explain it later on in this meeting. So they took this picture, and they did the following experiment. They took, this is the electron diffraction pattern, but they took this plate, shone a laser beam on it, and received an optical diffraction pattern. So on the right, you have optical diffraction pattern. On the left, this is the electron diffraction pattern. And they have 5-fold rotational symmetry. They are the same. Of course, you expect that. But they did something more. They took an aperture here and shrunk it. And while it was shrinking, this pattern of the optical diffraction disappeared for lack of information, but it did not change on the way on the way to disappear. It did not change. No twins. This is a property of the structure on the atomic level. Okay. Of course, nowadays you can take much better pictures, and here is an example of more modern picture taken by an electron microscope. This takes us into high-resolution microscopy, and Knut Urban later on in the meeting will talk a lot about it. High resolution has to do with phase contrast. Low resolution has to do with diffraction contrast. But diffraction contrast allows you to analyze the structure, allows you to analyze the defects to the greatest details. Everything you want to know about defects in a crystal can be very well analyzed by diffraction contrast in the electron microscope. It takes somebody who knows how to do that, and we'll talk a little bit about it later on. It's not something that you learn to do in 5 sessions on the electron microscope. 1984, by the way, take back. All this discovery was made while I was on sabbatical at NBS, National Bureau of Standards, in Maryland, in the United States, an amazing research institute that belongs to the Department of Commerce. And I spent there 2 years, from the end of 1981 to the end of 1983, then came back to Eternion. But in the summer of 1984, I went back to NBS, and I did that every year, almost ever since. And there I wrote this paper with Ilan Blech. Now, Ilan Blech was the first person who was willing to work with me at the Technion. After we wrote this paper, he left the Technion to go to California, and he's there now. And we wrote this paper on the structure of rapidly solidified aluminum-6 manganese. And in that large article was the chapter on the discovery. Those days, as an anecdote for the young people amongst you, scientists could not type. We could not type. We had secretaries that typed for us. We wrote by hand. They typed it. We corrected it. They typed it again. We corrected it again. They typed it again. And finally, the modern secretaries had IBM machines with a ball, not the click, click, click thing. No. Anyways, those days, we also sent the papers by mail. Yes, envelope, you write nicely, the address, stamp, and I sent it to Journal of Applied Physics. And a few weeks later, I received an envelope from the Journal of Applied Physics. My paper was there, our paper was there, with a letter, "Dear Dr. Shechtman, thank you so much for your contribution. We have decided not to send this paper for review because we feel that it will not be interesting for the community of physicists. Why don't you send it to another journal?" So I sent it to another journal. And that journal is Metallurgical Transactions. They accepted it and published it. But they published it. I sent it in September, October of 1984. They published it in June of 1985. Slow publication. Meantime, I am there, and I told my host, John Kahn, a famous scientist, thermodynamics person, I showed him the paper that was rejected. I asked him, what's so wrong with the paper? Why was it rejected? He read it, came back to me and said, "Danny, this is fantastic. We have to do something completely different. Just take your discovery from the first day, that information, without the Ilan Blech model, and publish it." I insisted that Ilan Blech will be in the publication. John Kahn invited another scientist from France called Denis Gratias, mathematical crystallographer. We sat down, we wrote a short paper, and we sent it to PRL, Physical Review Letters. They received it and published it in a few weeks. So the second paper was published first. When this paper was published, November 12, 1984, hell broke loose. I started to receive emails, telephones, you name it, from all over the world. "Danny, this is fantastic, fantastic." They repeated my experiments. I told exactly what I did, how do you prepare the material, everything. In 1 week, people around the world were working on the new structure of quasi-periodic materials, and they took my discovery and turned it into a fast-growing science with so many young avant-garde scientists, thousands of them around the world who did degrees on quasi-periodic materials. They made new materials. They studied their properties. Theoreticians went into outer space with mathematics and so on. As an anecdote, I can tell you that the first meeting on quasi-periodic materials, at the time we didn't know that it's the first meeting because we didn't know there will be second. But the first meeting was in Les Ouches, France. I don't know, many of you must know Les Ouches in France, wonderful place near Chamonix, ski. But there were 60 people there, and it was an amazing place because the mathematicians, the physicists, the chemists, the material scientists, the architects, we all met and we learned the lingo of the other professions. So it was an amazing place, and we started to talk the same language. All of us started to talk the same language that involved mathematics and chemistry and physics and so on. Okay, so this was the meeting in Les Ouches. And now I'll explain very shortly. Yeah, Les Ouches is a nice place. Very shortly. Many of the quasi-periodic crystals have icosahedral symmetry. This is an icosahedron. It's a platonic body, And if you put your eye up here and look down, you see that there is 5-fold rotational symmetry. Same here, 5-fold. Same here, 5-fold. This means that I only have half an hour, or what? More than half an hour, okay. Oh! If you put your eye here, where exactly where you are, you see 3-fold rotation symmetry, and so on. And the angle between this 5-fold and this 5-fold is exactly the angles between the diffraction patterns that I took in the electron microscope. This is why I called it icosahedral phase. Okay. So also, you can look at a football and see very beautifully, you know, footballs are made of patches, 5-fold patches and 6-fold, and that's how they look like. And you can clearly see beautiful 5-fold rotational symmetry here, 2-fold, 3-fold. And I bet you, whatever country you come from, whatever city, if you have a football team, I bet you they don't know they play with icosahedral symmetry. Shame. What is quasi-periodicity? To understand quasi-periodicity, we have to go to the 13th century, Leonardo Fibonacci de Pisa. His colleagues called him blockhead, but he was the greatest mathematician of his time, and hundreds of years later, he was still the greatest mathematician. Now, Leonardo Fibonacci de Pisa wrote a book, Liber Abaci, in the beginning of the 13th century. And in that book, he tried to convince the merchant of Pisa not to use the Roman numerals to do calculations because it is impossible. Use the Indo-Arab new writing and numerals, and then it will work. These are Indian numerals that the Arab merchants brought to Europe. And the book is an example how nice it is to use those Indian numerals. But in that book, there is a small chapter. And the small chapter I will talk to you about now. And this is him. Look at his eyes, wonderful. It's a drawing of him. And this is a picture, a real picture of a statue that he erected in his honor. And this statue is just behind the inclined Tower of Pisa. So if you go to see the inclined Tower of Pisa, again, all the towers in Pisa are inclined, but this one is very inclined. Behind it, there's a graveyard under a roof, and this, I'm not sure he's buried there, but the statue is there in his memory. So what did Leonardo say? Leonardo proposed, I'm talking about quasi-periodicity now, he proposed the following rabbit experiment. I will explain to you what are the rules of the rabbit experiment. Let's say that there's a female rabbit in the first month, and she has a husband or a boyfriend. He comes to visit, and now she's pregnant, and she will have a baby in the next month. So in the next month, here comes the baby. This repeats itself. She gives birth in the 3rd month to a little baby, and this baby has to mature because before somebody will come to visit her, and she can reproduce. So these are the rules. A mature mother gives birth to a little one grows up. So let's look at the 4th month. In the 4th month, 1, 2, 3, 4, yes. So this mother gives birth to a little one, this little one matures, and this mother gives birth to a little one. These are the rules. Now that you know the rules, there is order. What does it mean? It means that if you decide to continue this forever, you can do that. And if you don't make mistakes, everybody will get the same results. Why did I stop here? Because it was the end of the page. Okay. So these are the rules. The number on the left are the number of rabbits. These are all in each month. These are also called the Fibonacci numbers. And what's special about them is shown in the following two equations. Equation number 1 tells you that 1 plus 2 is 3. It also tells you that 8 plus 13 is 21, and so on. This is it. An equals an minus 1 plus an minus 2. What this tells you is that if n goes to infinity, then if you take the number of rabbits in the last row divided by the one before, you will get an irrational number tau, which is 1 plus root 5 divided by 2, known as the Fibonacci number, known as the golden mean. And if you talk to people of aesthetics, they will tell you that somebody who has the right ratio between the end of his nose and the belly button and so on, then that person is very beautiful, and don't argue with people who claim they understand aesthetics. Okay, so this is the Fibonacci. So where is the quasi-periodicity? Well, let's look at it. Let's see. Large, small, large, large, small. Large, small, large, large, small. But large, large, small. Large, small, large, large, small. There is no motif of any size that repeats itself periodically. No such motif that repeats itself periodically. And yet there is order. It is an order structure, one-dimensional order structure, which is quasi-periodic. This is an example of quasi-periodicity in one dimension. What about two dimensions? Two dimensions, and he published it in 1202. Two dimension, Penrose, Roger Penrose, an eminent scientist living in our time in England, a philosopher, physicist, chemist, mathematician, amazing person. And he designed these two tiles that can tile a two-dimensional space without gaps. And if you do that according to certain magic rules, you get this. You tile a two-dimensional space, and there are no gaps, and you can continue this forever if you follow the matching rules. Right? Another scientist named Alan Mackay, another eminent scientist living in England, our time, he is a crystallographer. He has a bright mind, and many years ago, he took Roger Penrose's picture, put it on a slide, took a picture of this, put it on a slide, and sent it to a friend of his, and that friend had a magnificent equipment. It was called a laser beam. He had a laser beam in his laboratory, and he asked him, would you please shine your laser beam on my slide and see the diffraction pattern, the optical diffraction pattern. His friend did it for him. He sent it to him. Lo and behold, 5-fold rotational symmetry diffraction pattern, sharp spots in the reciprocal space. Wow. But Alan Mackay published it in an obscure journal, and I did not, long before I did, I didn't know about this paper, so I could not relate to this. Okay, so this is Roger Penrose, Alan Mackay. What about quasi-periodicity in 3 dimensions? 1 dimension Fibonacci, 2 dimension Penrose, 3 dimension, voila, quasi-periodic crystal of the system magnesium, zinc, cerium, and you can see the beautiful 5-fold facets in this crystal. This is quite small, 2 microns, 3 microns, taken by one of my students, and we grew thousands of these things. Now, very soon, and I am answering one of you, I don't see, I'm answering you a question that you will ask me later. And the question is the following. The objection to my discovery was led by Linus Pauling, Professor Linus Pauling. We will get to Linus Pauling in a couple of minutes. But I want to explain you now what was his basic mistake, why he could not receive quasi-periodicity, why he claimed on that periodicity is enough to explain everything, and it's not. And in order to understand that, let's do some mathematics, not too complicated. And that mathematics says the following. I will say it, don't faint, it's simple. Let's take a high-dimensional space in mathematics, whatever you want, make a cut in this high-dimensional space, and project onto a lower dimensional space, and if the high-dimensional space is periodic and the cut is taken the right angle, then you receive a lower dimensional space which is quasi-periodic, and you're still alive. Great. Let me show you how simple this is. Here is a high-dimensional space, 2-dimensional space. I can make, clearly it is periodic. Let's say that in every intersection there is a mathematical point, no dimension, right? I can make a cut. The cut is a strip. I make a cut. And I send the strip not just in any direction, I send it in such a way that alpha is such that tangent alpha is the Fibonacci number tau. Okay, what does it mean? It means that if I start at a point here, this line will never ever meet any other point. Of course, because if it met a point, let's say that it met this point, go back. Let's say that it met this point here. It looks like, but it's not. Then the tangent will be this divided by this, which is a rational number. If it met a point, the tangent is a rational number. But I sent it to the irrational number. It will never meet any other point. Okay. Now what you do, you take all the points that are inside and you project them onto the one-dimensional space. That line, you project them on the line. And look what happened. Measure the distances. Large, large, small. Large, large, small. Large, small. Fibonacci rabbits. We took a periodic lattice in a high-dimensional space, 2 dimensions for you, cut and project it into a one-dimensional space, and lo and behold, you created quasi-periodic structure. What the mathematicians do, happily, in the evening, if they have time, they take a 6-dimensional space, which is periodic, make a cut in it, project it onto a 3-dimensional space, and create a new quasi-periodic structure. Does it exist in nature? Maybe yes, maybe no, but they can create whatever they want depending on the motifs in the 6-dimensional space. Enough of this. But why is it relevant to the objection? You see, okay. I will continue, then you understand. I repeat that experiment. This is what I did. Here we go, here we go. We did that. Now I bring red lines. Here are the red lines. The red lines are very close to the black lines, but not quite. They don't match. They don't hit each other because I made the red lines hit this point here. And so the tangent of the red line, the red alpha, the tangent is 11 divided by 7. You can count it, 11 divided by 7, which is a rational number. It's very close to being irrational. And the unit cell is this, from here to there. This is the size of the unit cell. And it repeats periodically. Okay. Now, if you want to get closer to the black lines, you can make a larger unit cell. Even a larger one will get you closer and closer and closer. And Linus Pauling insisted on rational numbers in crystallography. And therefore, when his models one by one were proved wrong, he said, okay, no problem. He always has something hidden here. Here is a larger model, and now it works. A week later, no, doesn't work. Okay, no problem. Here's the model. Here's the model. Getting closer and closer and closer to becoming quasi-periodic, but you can never reach irrational numbers by becoming closer to them by rational numbers. This was his basic fundamental mistake. He insisted on dividing two numbers. Okay, we now can continue. I call it years of rejection. 5 minutes. That's more than enough. Okay, I'll do that. Years of rejection. 1982 and 1984 were the years before, after discovery, before the publication, and I was at NBS, National Bureau of Standards. The reactions were varied. My friend John Kahn and some other people were very supportive. John came to my office and said, Danny, this is telling us something, and I challenge you to find out what it is. He didn't solve the problem, but he was encouraging. On the other extreme was totally negative. The head of my laboratory, different person, came to my office one day, smiling sheepishly, putting a book of X-ray crystallography, and he said, Dr. Shechtman, please read this book and you'll understand that what you're talking about cannot be. I said, thank you very much. You know, I teach at the Technion. I know this book. I teach by this book. I don't need to read it. I'm telling you, my material is not in the book. Took the book back. A few days later, came in and said, Dr. Shechtman, you're a disgrace on my group. I ask you to leave. My group. This was an administrative move. Don't faint. I just had to find another group leader who adopted the scientific orphan, and that was that. But this was the feeling, and if you want to see how I felt during that period of time, it was something like that. Okay, so this was the first period, 1980 to 94, 84 publication. And now the objection came from the International Union of Crystallography. Why is that? Because they insisted on X-ray diffraction. Don't talk to us about that electron diffraction, that we don't recognize that. I hope they recognize it now, because now electron diffraction is extremely accurate. And we could not give him, we, the whole community, could not give him X-ray diffraction because the crystals were too small and the X-ray beam were too large for the small crystal. Of course, now it's different. But in 1987, colleagues of mine in France and in Japan sent me beautiful pictures, and here they are, X-ray diffraction pattern, 5-fold, 3-fold, 2-fold, beautiful patterns. I took them to Australia, to Perth, the International Union of Crystallography meeting, 1987. And when I showed this picture, the community said, okay, Danny, now you're talking. They formed a committee that redefined crystals. Voila. So you would think, okay, who will object? International Union of Crystallography brings quasi-periodic material into the realm of crystals. Who will object? Not so fast. Because then there was Professor Pauling. I explained to you what his basic mistake. His rejection lasted for 10 years, and he was a great leader. He was really probably the greatest chemist, definitely in the United States, maybe in the world. He taught us so many things. He was a great scientist. But he made mistakes. It was not the first mistakes. And he insisted on developing larger and larger and larger models, which now you understand why he could never reach what he really wanted to. And he started 1984 until publication. 1994, he stopped because he died. And so that was the end of that. Okay, I want to mention a few names, seminal contribution. Roger Penrose, Alan Mackay, great. They're alive and with us, amazing people. Ian Blech, Denis Grasser, John Kahn, who wrote the first papers with me. John Kahn died a couple of years ago. Dov Levine, Paul Steinhardt are two scientists who developed the mathematical model, while the Blech model was the physical model. I think, for the sake of time, I want to tell you something more, but it's not important now. I wanted to show you the power of electron microscopy for discovering new things. Nothing is too small for an electron microscope, and there is nothing in crystallography that you cannot solve by an electron microscope. Thank you very much.